we'll go through these properties. We're starting with the order of integration. It says that the integral from a to b of f of x dx is equal to, now if you go from, say, we talked about this a little bit when we first introduced this in 6.1, if I go from, say, 0 to 1, and I switch it to go backwards, okay, to go from 1 to 0 instead, what does that do to the sign of the value of the integral? If you switch this, put b down here and a down here, f of x dx, it changes the sign to negative. So reversing the direction from a to b and then back to b to a will make it negative. That's the order of integration. That's the first of the properties there. That's just a definition. We also learned that the integral from, say, a to a of f of x dx is always equal to what? Saw this on the first lesson. 0, yeah. If I had taken the integral from 0 to 0 of the function 5 dx, I have no area underneath that constant or that line, and so it equals 0. Okay, it's also true that if you have the integral from a to b of some constant k times f of x dx, you can go ahead and move that constant out in front. So it's k, and there's the same thing for differentiation. I guess is still pretty easy. Those aren't too bad. Looks like they put the sum and difference together. So let's write that down and we'll talk about the sum and difference. We just used the sum formula on that problem number 48. Look it up. We did that with differentiation too. Remember, if you had a polynomial function, we could apply the derivative rules just one piece at a time. Same thing with the integral. So order of integration, we change the order, you change the limits of integration, flip them around, you have an opposite sign of whatever the integral is. Integral from a to a of a function is always 0. That's good to know. And a constant multiple, you have integral of some constant multiple times a function, you can factor that thing out and find the integral and then multiply it later. Those are all equivalent. So sum and difference says the integral from a to b of f of x plus g of x or minus g of x dx, we'll go ahead and combine them together. So integral from a to b of f of x plus or minus g of x dx is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. That's the sum and difference altogether. So if you have a polynomial function, you can find the integral of each one separately and then add up or subtract the values of each integral. All right, and then the additivity, here's what this says. It's the integral from a to, say, c of f of x dx is equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So if you have some integral that goes from, say, 0 to 5, you can break it up and take the integral from 0 to 3 and then from 3 to 5 is what that's saying. And then put them together and it's equivalent. So those first 5 you'll use a lot. And then the next 2 you don't use a ton. Like, they do make intuitive sense, but you won't use them a ton. So this is an inequality, it's an in-betweener. So you've got the integral from a to b of f of x dx is always going to be sandwiched in between the minimum value of the function f times b minus a, where b minus a is the length of the interval that you're integrating over, and max of f times b minus a. So that's the max-min inequality. And that the integral of the function is going to be between, if you took the minimum value of the function, so the way you get the minimum value is you might use derivatives, set the derivative equal to 0, find the minimum or the maximum. If you multiply that minimum value by the length of the interval, it will be less than or equal to the entire integral. And if you find the maximum value of the function, in other words, the highest y value, and you multiply that by the length of the interval, it will be above the integral from a to b of f of x dx.
Minus a around like
This is b minus a, right?
I thought it might be like that.
No, it's just b minus a. No, it's not an integral. It's just the max of the function is just the highest. It's the absolute max. It's the highest value it reaches on the interval from a to b. If you multiply that by the length of the interval, it's guaranteed to be more than the value of the integral. That's because that's like the hugest rectangle you could have underneath it, and the integral is going to be something less than that. And they have one final one they call domination here. Sorry, did you guys get all that? You get all of this? The last one's an inequality as well. So it just says, it's domination, but if f of x is greater than or equal to g of x on closed interval a to b, then the integral from a to b of f of x dx will be greater than or equal to the integral from a to b of g of x dx. I also have a clause in here about the fact that if f of x is strictly greater than 0, in other words, if the function is above the x-axis, always from a to b, then the integral will be positive. And we know that. As you're going from left to right, if it's above the x-axis, it will be positive. If it's below the x-axis, we learned it's negative as you're going from left to right. And if it was below the x-axis and you ran it backwards, it would actually turn back to positive. So it's kind of a combination of those. But those are the rules for definite integrals. And just like we saw in this problem number 48, we're going to use these rules and the integral value they give us to evaluate integrals. What's that? It's messy. Egg scrambled in there. All right. So let me ask you this before I give you this is another formula or rule, I guess. It's the average value theorem or average value. What must we check for when using any theorem in math? We'll go back to geometry. Go back to geometry. Go second. Go with that. You got it. Yeah, it fits all the requirements, right? It fits all the if part of it. And so what you'll find in calculus is that we have a lot of, here are the requirements for a lot of our theorems. It's if f is continuous on a sometimes closed interval, typically a closed interval, in this case it is closed. Sometimes it'll say if f is continuous on an open interval, it's given that. But usually continuous functions is what we deal with. So it goes back to the very beginning of this course. But you're right, we do need to check for that always. And here's what we've got. We've got what's called the average value theorem. Here's what the average value theorem is. And we saw this in 6.1 as well. It showed up. Actually, it was in that first worksheet I gave you, the accumulation stuff. And so the average value, remember that the integral is an accumulation. And you want to think of it as an accumulation. You're adding up all this stuff. So I gave you time versus velocity. And when we accumulated all those velocity outputs and multiplied it by the time interval, we had the integral. And then what did we do to get the average value? Yeah, we average it. We did division. Division by what? It was, actually, was it 2 in that one? I think it ended up being 12 because the entire interval was 12. You just divide by the length of the entire interval. So here's the thing. If, this is the average value theorem, but if f, it works like this. If f is continuous, that's right. So write this down. If f is continuous on a closed interval, we'll call it a to b. So don't go and trying to find the average value of a function that's not continuous. So some function, if it has a vertical asymptote or something like that in there, that's not going to work. If you run the interval a to b through a vertical asymptote, this will not work. You're going to accumulate a whole bunch of area there that you can't do anything with. So, but if f is continuous on a closed interval a, b, then at some point, call it C in AB, here's what's true. F of C, this should look familiar, equals 1 over b minus a times the integral from a to b of f of x dx. So f of c equals, in other words, they're saying if f is continuous on a closed interval, then there is an existence theorem, like the mean value theorem we saw for derivatives. Remember do you remember what the mean value theorem for derivatives was? F is continuous on a closed interval. There is a point C between A and B on a continuous function where the instantaneous rate of change, or f prime of C, equals the average rate of change, which is f of b minus f of a over b minus a. So that's the mean value theorem. Now this is the average value theorem for integrals. So some point C in AB, f of c equals 1 over b minus a, the integral from a to b of f of x dx. Now in the textbook, they actually just define average value. They use this little abbreviation, which I don't know if I've seen this before until this textbook, but it's average value of f. So it's AVF, average value of f, is equal to just this part of it. average value of f is equal to 1 over b minus a times the integral a to b of f of x dx. I think this makes sense because if you think about if I'm going to find an average test grade, I'm going to do what? I'm going to add them all up, right? And then divide by however many there are. That's what they're doing here. The integral is an accumulation function, so it's adding all this stuff up, and you're dividing by the length of the interval. So that's what average value is. So you'll have to know that. But average value is the right-hand side of this average value theorem. So let's do a couple examples where we find the average value. You have to have your calculators handy. So we haven't talked about how to find the integral of some of these functions. So here we go. A couple examples. Here's so let's see if we can find the average value of y equals x squared on 1 to 5. So if your calculator's handy, what's the formula say? Is x squared a continuous function? Yeah. On a closed interval? Yes. So the average value would be 1 over 4, or 5 minus 1, times the integral from 1 to 5 of x squared dx. We don't know how to find the integral of x squared dx analytically yet. So go ahead and find it on your calculator. What do you get? Your integral from 1 to 5. What can you tell me what the integral from 1 to 5 of x squared dx? Pretty big number, huh? What is it?
41.33. But we're getting.
So you, doesn't seem right. What did you guys get? Oh, that's what you get again for the average value? Okay. So the integral from 1 to 5 of x squared is, say it one more time, 41.3. Okay. Okay. So 41.3 or 41 1/3. And then you divided that by 4 to get the 10. What was it? 10. Okay, that makes sense. 10.3. So 10.3 is the average value. So what does that mean? What does that mean? Okay, at 1, I would be at 1. 2, I'd be up at 4. And it grows really fast. 3, 4, 5. Takes off. It's up here. So here we got this thing. Actually, it's all again. So here we have all this stuff. So that's what I just shaded in represents the integral from 1 to 5 of x squared. Right? 1 to 5 of x squared. I just drew the right half of the parabola and then just dropped in vertical lines between 1 and 5. So when I say find the average value, we got to about 10.3. So between 1 and 5, my average value for that function is about 10.3. So here's what the average value theorem says. It says that if this is a continuous function on a closed interval, there is some value c such that when you plug in that value to the function x squared, it equals this average value. Let me do another example here where we find that value c. So let me move this down. Yeah, this is a good one. So given y equals square root of x, I think we did this with the mean value theorem too. I think it was the same function. But given that y equals square root of x on 4 to 9, at what x coordinate does the function equal its average value? It's kind of weird thinking about average value of a curved function, but we want to find the average value of the function between 4 and 9. And according to our average value theorem, it says that there exists a c between 4 and 9 such that when you plug that c in to root x, it equals the average value. We're going to see if we can find that. So remember, just like it was with the mean value theorem, it's an existence formula, so you can't always find it. You can with this one. Here we go. Let me just draw a picture, a quick sketch of it. Quick sketch here. Square root of x looks like this. Now 4 to 9 here, 4 to 9. So the outputs would be 2 and then 3. This is up 2 and then up 3. So if I were to plug in 4, I would get 2, and if I plugged in 9, I would get 3. So let's go ahead and find the average value. So you got the integral from 4 to 9, so it'll be 1 over 9 minus 4, square root of x dx. Would you go ahead and give me the value that you get for this? So 1/5 of whatever that integral is, 4 to 9. Then we'll find the value c. Because this is a continuous function on a closed interval. So what x coordinate does this function equal its average value? You guys have a value? What do you guess? 2.53 re 2.53. So here's the deal. It says that at some point f of c is going to equal 2.53. F of c would just be square root of c. The function here is square root of x. And then can I solve that for c? You can on your calculator, right? Square each side. So c equals, what's 2.53 squared? 6.4. Okay, so what it's saying is that if you plug 6.4 into the function, if you found f of 6.4, which equals square root of 6.4, it will equal 2.53 value of this. 2.53 is the average value of that function, which makes sense if you go up here, back up here to our little picture. Remember that the output for 4 is 2 and the output for 9 is 3, so 2.53 is between those. It's not halfway in between. It's pretty close to halfway in between. Why is that? Going back to local linearity. Between 4 and 9, how linear is this function? Kind of linear, yeah, pretty linear. So if it were a linear function, 2.5 would exactly be the average value, right? It's halfway in between 3 and 4. This is not perfectly linear. It's curved. And so 2.53 is the average value. Does that make sense? So it's a way to get an average value for a function that's not linear. Like adding up 2 test scores and dividing by 2. Okay. So this is going to come into play actually quite a bit. Those rules of the domination and min-max doesn't really show up much in here, but this is going to show up quite a bit. I'll have some applications for you. So any questions on this? So we got like 7 different properties. This average value theorem, average value equation is this. One more, I think, here to look at. What is the average value of, here's a trig function here. What is the average value of y equals cosine of x on the interval from 0 to pi over 2? Why don't you go ahead and find that, please? Is there anybody who needs help on how to do it on the classic ones here? So Eva, does yours do the math type or did you figure out what order to put it in? You have the same thing. So you did as you go through. So you guys get the 0.63. You get 0.63 something. It's 0.637 to the nearest thousand. So we're getting it. 0.637. Yeah, that's it. Should be. So the setup looks like this. Just to make sure you got it. So it's 1 over pi over 2 integral from 0 to pi over 2 cosine of x dx. And you get about 0.637. So remember, cosine from 0 to pi over 2 would look like this. But it's just this region right here. That's it. From 0 to pi over 2. Just that region. So the average value on that is 0.637. Remember that up here it's at 1. The y-coordinate is 1. And down here it's at 0. So 0.637 is the average value between 0 and 1. It's a little bit more on the higher side, right? Above the 0.5. Because it's starting up high. That's the way it drops. All right. All right. I do have one more thing here. Nobody's asked me about this yet. I'm surprised. But we've been talking about continuous functions, right? What if it's not continuous? Can you still find the integral? Have you done any so far where they weren't continuous and you were still able to find the integral? Yeah. I think you did do one. What did you do to find the integral when it wasn't continuous? I think there was one. There should have been one. Was it the absolute value? Absolute value is still continuous. Oh, sorry. It's not differentiable because of the corner. There was one. So what did you do to find the integral of that value with the jump? Remember? Does the jump matter in terms of area underneath the curve? I mean, if I have a function that goes from, I've got a picture of it here. If I had a function that was like this, and then it jumped up here to say 5, and then just kept on going down over here. I mean, I could just draw a dashed line in there, find the area of this region 1 and this region 2, and there's my integral, right? So we can deal with it. Calculator might have issues with it because of the discontinuity, but we can still find the integral by breaking it up. And now that we know that integrals are additive, right, we could break it up into 2 different sets and then find the integral of each one and add them up. So sketch the graph. Can you sketch the graph of absolute value of x over x? You might have to graph it on your graphing calculator. But if you go to y equals, turn my statistical clock off on this guy. We go to y equals, sketch the graph of absolute value of x over x. You go to math, absolute value, it's under num, absolute value of x divided by x. And then graph it. I'm going to graph it in a standard graphing window. I still had my weird window. So what happens with this guy? Something like that. Discontinuous at x equals 0. Discontinuous at x equals 0. So here's the problem I run into. If I want to find the integral from -1 to 2 of absolute value of x over x, it runs right through the discontinuity at 0, right? So here's what I do. Color here. We're going to go, here's -1, and here is 2. So we've got this region right here call that region 1, and this region right here, we'll call that region 2. When you break it up in that way, it's pretty simple to find the integral. So we can handle it. It equals what? Area of this guy is, let's say, region 1 plus region 2 by picture. Area of region 1 is, be a little bit careful here. Remember, we're running it from left to right. And the area is below the x-axis. So the area is 1, but if it's signed area, what will it be? Negative 1. Plus, and then this guy, running from left to right, it's above, so it's just 2 by 1, or 2, which equals 1. Okay, now, try it on your calculator. Just try it. Let's see what we can do here. So go to math, number 9. Run the integral from -1 to 2. That function. Oh, did you get it? What's this thing doing? Did you get like 1 point with a bunch of zeros and some numbers on the end? Right? We just said it's 1. Would you agree that it's 1 up here? Like, where are they getting that? Do you have a 2, 2, 1, 2 or something like that? You might have said that. Is it? Okay. Do you all have that same? So the calculator is using an algorithm. It has figured out how to deal with this discontinuity. And it's pretty accurate. It's telling us it's about 1. But we know it's 1. I just proved it, right? So what's going on with the calculator? What's that? What's the calculator doing here?
It's not doing it right.
It is. What's the calculator? What method is the calculator using? Not the limit. It's just the calculator is using some kind of built-in approximation method. That's all. And so there's a little bit of error. Not very much. And it's pretty good. That's a lot of zeros before I hit that first 2. So the calculator handled that one. But that's how you can handle something that has a discontinuity. For example here, let's see. So to find the value of a function with a jump discontinuity, we can just break it up. Split them up. Okay, so you'll run into that and see inside. So I thought it'd be helpful if you could actually do this in class. This is going to bring you right up to our kicker, which will come on Thursday, and that is the fundamental theorem of calculus. So understanding this well, as well as the previous 2 homework assignments, is going to really help you to know what's going on and introduce the fundamental theorem of calculus. It's a calculus class. It's the fundamental theorem of this class. It's kind of important. And then after I introduce the fundamental theorem of calculus, it's like it opens up just the floodgates for practice problems we can do. Because once you understand what that says and its application, then we're there. So I'm going to start showing you some pre-response questions. Oh, that's cool. Here's the picture. Yeah, cool. Mine doesn't do that, but
I'm excited to learn the fundamental